Hello everyone and welcome to another World Cement webinar. I'm your host David Bisley, Senior Editor of World Cement. Joining me today is Hans-Georg Conrads, CEO of PROMECON. Hans founded PROMECON and has invented numerous measurement systems for the power, cement and smelter industries. Today these measurement systems are installed in hundreds of plants around the world. And of course, the reason for today's webinar is his presentation entitled Cement Plants, Potential and Challenges of Efficient Gas Flow Measurement. In this presentation, Hans will explain how accurate gas flow measurement, particularly of tertiary air, is essential for optimizing fuel use, controlling emissions, and maintaining a stable and efficient cement production process. And as always, we'll be holding a live Q&A session immediately after the presentation, so do make sure to join us for that and take advantage of our live technical expert. To take part in the Q&A, it's very easy. Simply click on the Q&A tab on the right-hand side of your screen and type your question in. And you can actually submit questions at any time during the presentation, so don't leave something to chance in case you forget it. Type that question in and we'll pick it up at the Q&A later. Speaking of questions, to kick things off today, we have a brief poll for you. It's a very simple question and it's very easy to take part. If it hasn't already appeared on your screens, click the poll tab to the right of your screen and give us your answer. Please do take part, as we'd love to have your feedback. So, as I said, very simple question for you. Do you have a PROMECON system in your plant or experience using one? Yes or no? So we'll let a few more results tick in. Okay, so just to repeat that question for you all. Do you have a PROMECON system in your plant or experience using one? Yes or no? Okay, interesting. So we've got a little bit of a mix there. We've got some hopefully satisfied customers as well as a load of potential customers there as well. So without further ado then, I'm going to hand things over to Hans to have a look at and discuss those results and get his presentation underway. Hans, the floor is yours.
Well, thank you very much, David, for this kind introduction. I welcome you to this webinar today to talk about gas flow and potential challenges in cement plants. Cement plants are basically one of our main markets and our main targets for our business. We've been measuring gas flows in large cement kilns, in the pyro string, in the pulverizer sections for tens of years. So we've been seeing quite a lot of issues and solved a lot of problems for people. Basically, our company is active in a couple of industries. We started in 1995, so we're just heading for our 30th anniversary next year. We're located in Barleben, which is a small village close to the wonderful city of Magdeburg, Germany, about 1.5 hours west of Berlin. We are manufacturing process and measurement technology for power, cement, waste to energy and smelter industries. And of course, today we are focusing only on cement, where we help clients to increase availability, save energy and money. I will explain how we do that and why it is important to know your gas flows. But before we start that, just a brief look at where we have been with the cement technology. As you can see, pretty much all around the world, there are areas where we are more intensely, of course, Europe, United States. But in recent years, lots of Africa. Africa has come up on the map quite strongly. India, of course, Middle East, in Asia, even down to Australia, and of course, a very new and interesting market, South and Middle America. Now, in order to start this thing off, I don't need to tell you so much as engineers in cement plants or operators of cement plants. There's nearly no gas flow in your plant that is not dust-laden. So all your flows basically are dirty and dusty. And this for us basically constitutes process gas conditions. We are a company specialized on process gas. Now, what is process gas by definition? For us, process gas means hot gas, it means dusty or dirty gas, and it means large ducts. So this is really the difference to most of the other gas flow measurements in the world. Process gas measurement is rare. You don't have many systems out there in the industry that can really measure process gas as I have defined it. So gas that can be 100 degrees C, but could also be 1,000 degrees C, even 2,000 degrees C. Gas that can have up to 100 grams of dust per cubic meter, not 100 milligrams. So these are all conditions that we are very well acquainted with and that we have developed our special measurement technology for. In order for you to give you an example, please take a look at the picture at the lower right-hand side, where someone has taken out one of our sensors out of the gas duct. You can see that the sensor is completely covered with clinker dust or with raw meal dust. And as you can see, this sensor needs no cleaning in order to measure properly. Sensors that are covered like this can measure perfectly with perfect accuracy. There's no need to clean or to recalibrate them. And that's the main feature and the main value of our measurement. It is that you put it in, it's digital, and it doesn't drift, and therefore you always get an accurate result over long term, and there's no regular need for maintenance for this measurement. And why this is so, I would like to explain in the following slides. Our system consists out of two sensors, and these two sensors are basically nothing else than an antenna. The dusty gases that flow through your ducting are usually electrostatically charged. So they all carry a charge that moves by our sensor. And you can see, if you look at one sensor, let's say the lower one, you can see a succession of clouds of dust passing by the sensor. And these clouds have a change in density. So the charge that is passing by the sensor is also changing over time. And this change over time induces a current, which we call time signature. The current over time. If you look at sensor 1, you can see the current that would be imposed on the sensor over a typical second of measurement. Now there's a second sensor which is downstream, which is in this picture called sensor 2. And this sensor 2 basically picks up a very similar time signature. And the reason for that is simply the flow pattern between sensor 1 and sensor 2 will not change dramatically. It will pretty much be the same like on sensor 1. It will be very similar. So if you take these two time signatures and you just match them and overlap them, you will see they are very similar. You can see it with your bare eyes. But of course, you can also see they're time shifted because the sensors do not sit at the same location. One sensor sits upstream, the other sensor sits downstream. And therefore, you can definitely see a time shift between the signals. Now, once we have these signals recorded and digitized, the question is, how do we find out this time shift? And the way we do that is fairly simple. We just measure the relative overlap of the signals. And since these signals are random, the overlap, if you have some time shift between them, should be very small. The resulting overlap should be small. And if you now start to shift the functions towards each other, you should get a cross-correlation function that is, again, pretty much a noise function, or with some frequencies in it, but it will still be a fairly small value of overlap. But on one period of time, on one point in time, you will see a sharp maximum. Let's have a look at that. We put this thing into a cross-correlation filter. You look at the cross-correlation function, and here you can see at 52 milliseconds, you have a maximum in overlap between the two functions. And you can see that in the correlation function as a sharp maximum. So here we have our measurement principle. We record the signals on two sensors. We see flow patterns on two sensors. We digitize the signals. We put them into a cross-correlation filter that overlaps those two signals and shifts them in time. And it looks at the relative maximum overlap between the two functions. And this is what you see here. Now, this 52.1 milliseconds in this example represent the time shift between the two measurement signals, and hence the time of flight of the gas between sensor 1 and sensor 2. And that pretty much is already it. So you divide the distance of the sensor, let's say 300 millimeters, by the time of flight, 52 milliseconds, and out you get meters per second. Very simple, right? So you have millimeters divided by milliseconds gives you meters per second. And that's basically the velocity of the gas in the duct. Now, this method of measurement is radically different from other methods, such as delta pressure measurement, which is basically measuring the pressure if you put a venturi into the duct, or if you put a pitot tube into the duct. It is also vastly different from any type of advanced measurement, such as ultrasonic or thermal anemometers. What we do here is we look at the direct pattern over time, we digitize, and we measure the time of flight directly by the cross-correlation calculation. And the big advantage of this measurement is that it is only dependent on time. There's no other variable in this equation except time. And B, the distance is fixed by the sensors, and the sensors reach into the duct perpendicularly to the axis of the duct. And that is a big advantage as well, because we're measuring a vector. Our velocity is not a scalar value, but it's a vector, and the direction of that vector is pointing parallel to the duct. So if you have swirl in the duct or any other lateral component of flow, this will not be detected by our sensors. Our sensors will only measure the velocity in direction of a duct. And that is a very big advantage because it gives you the true throughput through a duct. What you can do then, of course, is you can compensate the measured velocity by the temperature of the gas and the barometric pressure. And of course, you should also take into consideration the cross-sectional area of the duct that this whole thing is happening in. So you have cross-sectional area times velocity gives you actual flow. And then compensation by barometric pressure and temperature gives you STP flow, standardized temperature and pressure flow. That's it. So what you do is you have this adapter and you weld it on to the duct, you put the sensors in, and then what you get is a time of flight, which you can then multiply with the cross-section area, compensate for temperature and pressure, and there you have your measurement. A few things are important. One thing is that the sensors have a known distance. In this case, we're talking 350 millimeters. Another thing that, of course, is important is that the sensors are aligned. We don't like twisted sensors, because then whatever flows by sensor 1 does not flow by sensor 2 maybe. And if they are twisted such that they are not parallel, you will also have the danger of a change in distance of the sensor. The average distance of the sensor changes, you will induce a linear error. In order to prevent that, we have these mounting brackets. The mounting brackets have a fixed distance, and the mounting brackets are parallel, so that the sensor is looking down parallel. The other thing you should mention is that you have enough ID upstream distance. The downstream distance for us is not important because we are not measuring any pressure changes. For us, pressure change is not an issue, right? The only pressure we need is the barometric pressure. Whether the pressure is a few millibars up or down will not change the density of the air significantly. So barometric pressure is enough. And then, of course, for density, the big thing is temperature. If you have a duct with a venturi-like zone, so you have a duct that has a tapered section inside, then, of course, that section is the best possible place for us to measure. If you don't have that, such as on a downcomer, You just mount our sensors on the downcomer directly, and then you make sure you have enough upstream IDs so that we can then have a straight flow around the sensors, and we can measure your velocity. So this is how the whole thing looks like. You have a box. The box has two connections for the sensors. The raw signals go straight into the box and are calculated into a cross correlation. The box itself has a power supply, 24 volt DC, AC, or 230 volt AC. I need to say 230 volt is not correct. It's actually 63 volts up to 250. So wherever you are, whether you are 50 hertz or 60 hertz, whether it's US or it's European system, it doesn't really matter. And then besides the ground, we also have an output for the 4 to 20 milliamp signal, which contains system fault below 4 milliamps. So you can also detect when there's any fault. For example, if somebody cuts the cable or something, you will get a signal for a fault. That's pretty much it, because there's not much that you have to do in order to check plausibility on drift or on zero. You know, for example, we don't have any zero. If you have a delta P measurement, you always have a 0 point that you need to check for drift. Now, what's the time of flight between sensor 1 and sensor 2 if the velocity is 0? You know, the time of flight gets infinite. The time of flight is infinite if velocity is 0. So there is no 0 point for us to check. And since we're measuring time only, the measurement is strictly linear by definition. So linearity and 0 are two things that just don't have to be checked with this measurement by definition. And therefore, all these points just are a no headache for you. Now, this is the most common system that people have in their cement plants. This is our biggest seller for downcomer, for raw mill, for clinker cooler, for calciner. I mean, this box is pretty much the most likely sold box. We have boxes with multiple channels, but usually people buy single channel box for an application. Now, I'm showing you something else which is probably not so relevant for your plant. What happens if you don't have dust? For example, what if you have absolutely clean air and clean gas? Then in this case, we have a range extender that can ionize the gas. And this ionization allows our system to measure the flow the same way as if there was dust in the gas, right? This is something that we usually are using for applications where you have batch applications, or in power stations where you have clean air going through the mills. In cement plants, usually there is no need for a range extender, because in cement plant, usually the gas is so dusty that it's always easy to measure. And there is no condition where you have really clean gas. When you are measuring the dedusting system of a copper plant or a steel plant, you sometimes have fairly clean air, and then you have very dusty air. So for this, we have this range extender, but I guess in cement plant, it's not such a big demand for it. So what can we say about the measurement? The measurement range goes from above ambient. So whenever you have, let's say, starting from 50, 60 degrees, goes up to 2000 degrees Celsius. In this version that I'm showing you here, the version with the antenna, we can go up to 2000 degrees Celsius, to 1000 degrees Celsius. So up to tertiary air temperature levels. The velocity range is from 3 meters per second up to 100 meters per second, strictly linear. Strictly linear. We have a turn down ratio in this way over 20. There's no other delta P measurement that can show a turn down ratio of that sort. The dust concentration range with the range extenders from 0 milligrams to 3000 grams. So 0 milligrams to 3,000 grams per cubic meter. If you don't have the range extender, you should have something like at least 1 milligram of dust in your gas flow, which is usually the case. Accuracy typically is 2% full span. Of course, this depends a little bit. If you are mounting our system directly after a bend, of course, you have to analyze how representative our measurement is in that location. But if you look at a long duct, as you can see in the background of this, the nice long tertiary duct, you don't have this issue. Maybe also I should mention here the flow profile, very important. We have two sensors that reach far into the duct. However, the flow profile in your application usually is a very flat profile. Remember, you have 20, 30 meters per second of gas velocity. And at these high gas velocities and these high temperatures, you do not have the typical parabolical laminar flow profile. You usually have a very flat profile, which is just caused by the high level of turbulence of the flow. So the antennas have a very representative measurement accuracy on long straights. If you have bends, then we have to analyze the thing, and maybe we have to put in 2 pairs of sensors so we can average what we see. So that's it on accuracy. Repeatability, I don't need to say much. It's way better than you will ever need. So the system will run with one calibration for its lifetime. There will be no recalibration for any of this. So it will simply go on forever. Reaction time is faster than a second. So every second you have a new value. 420 milliamps IP66 protection. Well, the advantages, again, no K factors, no calibration, no drift, no duct modification, and no regular cleaning or maintenance. Now, years ago, we've done a lot of comparative measurements. Here is one example with the VDZ, the German Association of Cement Producers. They did a grid measurement with their SP tow tube here on this large downcomer. No, I think this was a bypass. And the result was very good. Our measurement is extremely accurate. We also have done a comparative measurement with Deutsche TÜV on a similar duct. In fact, that was a stack. And that was for Qual 1 certification. And Deutsche TÜV said it's the most accurate system they've ever tested in a large duct like this. And this has to do not only with the digital measurement, but also with the fact that we have a vector measurement. Remember, the two antennas, they stick into the duct perpendicular. Perpendicular means they are perpendicular on the longitudinal axis of the duct. And that means that is the vector that they will measure. They will measure a time, and the distance that is used in order to calculate the velocity is a vector. It's the vector that stands perpendicular on the two sensor antennas. So I think that explains pretty much what this thing does. It's not so much to explain because it's fairly simple. If you want to put it in a nutshell, the way we measure is a digital way that the police used to measure car velocity in ancient times, like a little police trap. You have 2 points that you cross, and out of the timing, they know your speed. That's pretty much what we do. What can you do with this in a cement plant? And I have taken out a couple of applications that keep on repeating when customers ask us, what can we do in order to help them with their gas flow management? It has been about efficiency, about process noise reduction, about fan power reduction, about lowering fuel use, about lowering NOx in the calciner. I guess in the future it will also be additional things such as waste heat recovery control, such as controlling CO2 abatement process. I think the cement industry is on the complete new verge of decarbonizing, and decarbonizing means for most cement plants, they have to strip down the CO2. And for this, gas flow analysis, gas flow measurement is essential. And we are currently having several projects where large companies are doing pilot plants where they need accurate gas flow measurement, as well as more gas characteristics. So I think PROMECON will expand into this field in the next years quite significantly, because we see a huge rising demand in the future for cement plant gas flow management. But what we have done in the past, you can see on the slide. We have done raw mill optimization at several points, and I will go into the details of that. We looked at bypass control. We looked at downcomer, of course, a very important part of our sales into the cement industry is downcomer. And then, of course, we have looked into clinker cooler. Highly interesting, especially if you want to do the balance in the clinker cooler, but also if you like to measure individual flows out of the clinker cooler, such as waste heat recovery. And then, of course, one very pivotal measurement is tertiary air measurement and control, in order to control calciner combustion much better. So, yeah, we want to discuss how can you save money with this measurement. I've taken out a few examples that we can go through. The first one is quite common application, raw mill. Raw mill, a huge energy drain in your plant, huge consumer of electricity, but like all milling plants, the grinding power and the grinding of the material is only a small portion of the total electricity consumption. One very large factor in electricity consumption is just fan power. So moving the dusty gases around is at least as electricity consuming as grinding them. So fan power is a critical thing. If you have a raw mill, of course, you put in the material, then you put in the gas in order to dry the material and also to move the material past the classifier and transport it then to the baghouse filter. So the gas has three purposes: drying, classifying, and moving the material, moving the solid material. And of course, gas flow and gas condition are critical to the operation of the raw mill. Now, the experience is that in many cases, the raw mill gas flow is on the high side, and that brings a potential for optimizing the gas flow through the raw mill. Let's look at the problem itself. The raw mill fan has to be operated in such a way that a specific airflow is achieved. And the most important target is to keep the mill running, right? So if the airflow is too low, then you are running the danger that not enough material can pass the classifier, and as a result, the material will get higher and higher on the roller table, and therefore the rollers will basically drown in the material, and that will lead to a trip of the mill. And the trip of a mill, especially with a raw mill, is not a very entertaining experience. It's a very large machine. Cleaning out the mill is a fairly tedious exercise. Some mills have automated that, but still it is an event that no one likes. Now, as a result, many operators are running the mill on the high end, and you can see that there's a certain security factor in here. You're running the gas flow 10-15% too high. Now that has consequences for the classification of the material. And of course, that has consequences for the baghouse because you have more gas than is actually needed. For a baghouse, a low gas flow is actually better because you have a better separation of solid material from gas. But on top of it all, of course, is your fan power. Most modern plants have large fans with variable frequency drives. And these large fan drives are non-linear with the gas flow. So if you require a certain amount of gas flow and you increase it, the increase in power will be by the third order. So if you need 10% more gas flow than actually needed, the power of the ID fan goes far larger than this. You're talking 25, 27% more fan power just to raise the gas flow by 10%. Now, if you look at the size of the fans that you have, especially on the raw mill, these are big fans. You know, we're talking fans about 1 megawatt electricity. Now, there are a couple of things here that give you a problem. One is, of course, electricity bill is one thing, electricity cost. The other thing is that you might also limit your ability to run the mill at full load. So also capacity factor comes into play. So the solution, of course, is fairly simple. The solution is that you measure the airflow accurately so that the operator can trust the airflow and can reduce the safety margin that he's overdrafting the mill with. And this security factor gives you back a lot of savings. The savings that you're usually looking at with typical mill size would be 1 kilowatt hour per ton of grinding material. So we're talking here about 1,000 hours, 2,000 hours of return on investment for a mill. Not much. So a very small measurement that is accurate will give you a big saving on the mill. The next application I would like to discuss with you is downcomer. Downcomer is our most popular application. We have many, many systems out there that are measuring downcomer. Why is downcomer so important? Of course, the downcomer gas flow is initiated by the ID fan that sits on the bottom of the downcomer. So you have basically on the other side of the cooling tower your rotary kiln. The rotary kiln has an off gas that goes through the riser duct, goes through the calcining process, and then goes all the way to the cyclone, the cyclone preheaters. So it goes from cyclone preheater to cyclone preheater, and finally it ends up at the top stage where it then is pulled down in the downcomer duct. So this gas contains the rotary kiln gas. So it's important how much gas goes through this downcomer duct. It's basically the gas that is also going through the kiln, plus the gas coming from the tertiary air duct. How do you control this gas flow? I mean, usually people take an oxygen sample on the kiln inlet in order to see how much oxygen level they have in the rotary kiln, because that is a very important measure in order to keep the kiln at the right stoichiometry. You don't want to have reduced atmosphere in the kiln. You don't want to overdraft the kiln. So it's right. Again, it's an optimization process. You would like to have the right amount of gas flow. And that is usually measured by the O2. Now, this O2 measurement is essential, and the PROMECON measurement will not replace the O2 measurement. The O2 measurement will always be needed. However, the O2 measurement is not a very good measurement to control the ID fan, because the O2 measurement is slow, and if you measure it too far downstream, then also you have too much leakage air from the cyclones, and that would result in the fact that also your O2 levels are fairly high, and the measurement has a very bad error behavior. So what our customers usually do is they take the O2 measurement as a long-term trend in order to keep the mill, to keep the rotary kiln at the right stoichiometry. And they add one measurement on the downcomer that you can see there, the PROMECON measurement, in order to have a short-term fan control that allows them to reduce process noise and have a far better regulation of the total gas flow through the kiln. So you can have either your gas analyzer at the gooseneck. Some people have an analyzer even in the kiln itself. But the unavoidable fluctuating heating values of the fuels will not give you a perfect control value for your fan. And this is necessary. So the solution here to the problem is that you have an additional measurement. You have a cascaded controller, and one value going into the cascaded controller, of course, is the O2 value, and the other value, the short-term value, is the gas flow through the downcomer coming from the PROMECON measurement. And this is a big savior in fuel costs. So the total savings that you can achieve here would be around 5% due to more steady kiln operation. Remember, this also includes fan power. Never forget fan power. If you have process noise, so your fans are going up and down and up and down, and all your fans have variable frequency drives, so you have a third order magnitude increase with power, you can easily calculate that the variation of power is not symmetrical. In other words, it's not like you save the electricity on the down cycle that you lose on the up cycle, but you always lose far more electricity on the up cycle. So therefore, making a fan or any control loop run flatlined will always save you energy on the fan, always, automatically. So on a 3,000 ton per day kiln, yeah, I mean the savings are gigantic. We're talking tens of thousands per month. Again, if you put this in, you tie it into your control loop, you can get this investment back in very short time. Now, TAD. TAD is one of the most critical measurements when it comes to controlling precalciner. The precalciner gets its oxygen in large quantities from the TAD, and the tertiary air duct measurement is essential to control the overall stoichiometry, and therefore the NOx formation in the precalciner. Precalciner is a big NOx source and therefore difficult to handle, to manage. Now again, here we have a measurement that goes straight into the tertiary air duct. I need to say something to you that I have not mentioned yet, which is new. Besides the antenna measurement that we have, that I have talked about, PROMECON also has an infrared measurement that we are offering, especially for tertiary air ducts that have a very high dust level contact, because it can be very abrasive, can be very hard to measure. And we found that the infrared measurement is a perfect measurement for this application. On top of that, you can get additional benefits such as temperature. And we are also looking into more elements that you might be able to measure at that location in the future. So tertiary air measurement is a very hot candidate for more applications in the future than just flow. But for now, what we are giving you is flow into the precalciner. And the main issue here is, of course, to control the hot gas flow into the precalciner to avoid peaks in NOx formation, peaks in temperature, and to have a more steady process, and also to close the balance over your pyro string. Close the balance of your pyro process. So you can regulate the load on the precalciner. You can check how much fuel you put into the precalciner as in comparison to your airflow. You can stabilize the process. Some people even have dampers on their precalciner, but also even without that, you have the chance to control the fuel flow to the calciner, also based on the tertiary airflow and kiln flow. This will stabilize the process, so it will allow you to use more alternative fuels and lower your fuel costs. And it will also mitigate problems such as NOx formation or other process variables that you want to tackle. Last but not least, another thing that we have been asked for several times is the the balance of the clinker cooler. You have at least 5 or 6 fans that blow cold air into the clinker cooler. And then you have several branch-offs that come out of the clinker cooler. You have the waste heat recovery, you have the tertiary air that's branching off. So you have several airflows that go out of the clinker cooler. Now, one big flow, of course, goes undetected, and that is the main gas flow, which is the secondary air into the rotary kiln. You have no idea of what the secondary air into the rotary kiln is because you can't measure it. And even if you measure it downstream in the downcomer, you already have the tertiary air added, you have leakages of the cyclones. So wouldn't it be nice to know the secondary airflow through your kiln? A very important parameter. If you measure tertiary air and waste heat recovery and all the branch-offs, and you measure the cold air into your clinker cooler, you can have a fairly good trend value of the secondary air that goes through your rotary kiln. So the ID fan, of course, has to be operated so that a specific flow through the kiln is achieved. This is usually checked by the O2 measurement at the kiln inlet. However, again here, an additional measurement that gives you a rapid reading of the secondary airflow into the kiln helps you to balance your kiln combustion air. It helps you to balance your clinker cooler. Yeah, is all the air going to one side, or is the clinker cooler balanced and has the neutral zone in the middle? So all of this can be controlled far better by having a good mass energy balance over your clinker cooler. Remember, you have 2 ID fans, one at each side, one at the waste heat side and one at the downcomer side. And these ID fans need to be balanced, and a good gas flow balance in the clinker cooler is a big help for achieving this balance. And what's the benefit? The benefit, again, is a much better regulation. It is reduction of process noise. It is a lower energy consumption and a lower fuel consumption. Okay, recently quite a few projects came along that dealt with waste heat recovery. Waste heat recovery is becoming bigger and bigger. More and more countries demand the use of the waste heat, and we have several OEMs that are building waste heat recovery systems for cement plants, which are inquiring our meters regularly. Because if you have a waste heat recovery boiler, you want to know the gas enthalpy going through the boiler on one hand, and you would like to know the water enthalpy going on the other end. And this will allow you to establish a measure for the cleanliness of the boiler, to see how effective the boiler is working. And our measurements have been retrofitted to quite a few plants, especially when they add a waste heat recovery system. So if you are adding something to your plant and the manufacturer of the waste heat recovery system tells you, I can't measure your gas flow, you tell them, yes, you can, because we have quite a few of examples and references that show our waste heat recovery measurements. So you can measure the gas that's going into the boiler and out of the boiler. You can do, of course, a measurement of the temperature of the gas and the temperature loss. And that will then, of course, give you a mass and the possibility for a good mass energy balance. In most boilers, people measure, temperature, but you're missing the flow, right? So, I mean, in coal boilers, you can also measure the O2. So you measure the O2 level, and that tells you about the stoichiometry. But in a waste heat recovery boiler, you are not combusting anything. There's no combustion. So the typical O2 measurement that helps you to check the efficiency of your waste heat recovery boiler is not helping you. The only thing that's helping you is temperature and the flow. Because temperature and flow give you the enthalpy that goes into the boiler and the enthalpy that goes out of the boiler. So you can see how much energy the boiler has been able to get out of the waste heat gas. So that brings me to the end of my presentation. I would like to reiterate a little bit the main motivations. We don't need to talk much about pitot tubes because I have not seen much pitot tubes in cement plants. Pitot tubes block. Some cement plants try to help themselves with ultrasonic measurements, or they try to use hot wire anemometers, which are also not a good idea. Hot wire anemometers are very, very good at cold air, at liquids, but not at hot air, and especially not at dirty air. Then, of course, modifications that you have to do to your pipe are difficult. So the reality is, most of the cement plants do not have gas flow measurement. Most of the cement plants are working with pressure and temperature, and that's it. There is no idea of where the gas goes. And in recent years, more and more people, more and more clients that we have been working with have understood that the gas flow is a pivotal part if you want to make your cement plant more environmental friendly. And if you want to make it green one day, so you would like to do CO2 sequestration, you will have to measure the gas flow. You will also have to measure the CO2 content, which is something that PROMECON can also do for you. So you can measure gas flow and gas composition, gas temperature. We are the process gas flow measurement company of this world. There's no company in this world where you will find hot gas measurement flow capabilities like you will find at PROMECON. We are very specialized. This is a very special segment, but it's increasing in value and in importance all over the world. Here you can see a few of the clients that we have, but some of them are quite heavyweights, and we always have been very happy to work with any of them. And we have, of course, far more clients than these, but we'd be happy to have you as client in the future. If you have a cement plant, we will have the possibility to help you and optimize your plant 100%. Thank you very much for your attention.
Okay, Hans, thank you so much for the presentation. It is now time for our live Q&A session. And as I mentioned earlier, for you guys in the audience, this is a fantastic opportunity to get your questions answered by an industry expert. And if you have just joined us or are still getting used to our new webinar platform, submitting a question is really very easy. Simply click the Q&A tab on the right-hand side of your screen and type your question in. Now is the opportunity to get your questions in and take advantage of Hans's expertise, so do make sure to take part. And as always, we'll try and get through as many questions as we can in the available time. But please don't worry if we don't get around to covering all of your questions live, as everything will be passed on to the team at PROMECON and they'll be able to get back to you in due course. I have just noticed a very quick question that I think is actually unusually directed at me. Will the presentation be available? Yes, after the webinar, we'll be providing an on-demand link to the presentation, so you can go through everything at your leisure as well. But to get on with the actual questions for Hans, so starting off then, I think you touched upon this a bit in your presentation, but how difficult or what is the difficulty like of installation? You know, how long does it take?
Yeah, I think one could see in the presentation, we have this bracket, this mounting bracket, which is basically two sockets that you weld on to your duct. So what you have to do is you drill two holes, you weld on the mounting bracket, and that's it. You put the sensors in, put the cables on, put the box on, and if you switch it on, you should see a velocity. So it's fairly straightforward. You have to modify your duct, but usually with clients that is not a big issue. So no big modification that you have to do. How long does it take? If the plant is down, you can get to the duct. It's, I would say, with all the bells and whistles, it's a shift. It's not more than that.
Okay. And related to that, actually, does installation have to take place whilst the plant is down then?
Most people do that. We also have clients that say, oh, we can do this while the plant is running. We have negative pressure in our pipe. If then with special care and special protection, we can We can weld the bracket on, and after that we drill a hole through that. Yes, but the usual procedure is that people wait for a short outage, doesn't take long, and then they put it on.
Okay, excellent. And can you remind us how often you might need to recalibrate the system or perform any kind of maintenance?
Recalibration, never. It's really a lifetime calibration, because it's like unfortunately only have a mechanical watch here, but many people have digital clocks. And how often do you recalibrate them? How often do you bring them to the watchmaker to repair them? They are just lifetime devices. They would, and this is all we do. We have a clock in our system, and the clock ticks out how fast this whole thing is flowing. That's the only variable. So absolutely drift stable. That's the biggest ticket. That's why we're on process gas. There's no need for recalibration of this system over the whole lifetime.
Okay, excellent. Moving slightly towards maintenance as well, we had a question come in here from Min Zaya, who's asked, may I know wear issues related to the sensor? Do you have any experience with this case?
Yes. Let's divide the world into cold and hot gas.
Okay.
For PROMECON, cold gas is anything up to 600 degrees Celsius. That's the cold side. Anything above 600 to 2000 is hot. Now for cold, we have materials for every gas flow. I must say, for raw meal, there's not special material that we need. We have just hardened steel or stainless, and that lasts for many, many years. We don't see wear issues. When it comes to hot, the main question here really starts with TAD. On TAD, sometimes they say they have 1000 degrees Celsius, but the truth is, in many process, a lot of times in the process, the temperature is significantly higher. It's not 1000 degrees C, it's 1200 and 1300 degrees C. So every 10 degrees C, every 10 Kelvin, in such a hot environment are, of course, putting stress on the steel and stress on the antenna. So we have several plants where we have now installed what we call an infrared sensor, which I was not talking about today, but I'll be happy to do so on the next webinar. It's a fairly new development. An infrared sensor basically does not protrude into the duct. It just looks from the outside, and it correlates the infrared light the same way that the electrostatic sensor does. And we have installed that in a couple of plants now, and of course there is absolutely no wear issue with that. And that measurement will also allow us to do more in the future, such as temperature and gas composition. So I think for tertiary air duct, PROMECON is heading into the direction of infrared in order to have the wear issue mitigated. And then I don't see big wear issues. These are the wear issues that, the high temperature side. And I think we have a good solution for that.
Okay, and just to clarify, the infrared system, that is currently available, or is that?
Yes, that is available, and it works with the same box. It's just that the sensors do not have an antenna, but they just have a sleeve that you put onto the duct, and then you just look inside the process.
Okay, excellent. Now, we mentioned the potential measurement of other factors as well. We had a question here asking whether it be possible to include measurement of pollutants such as acids, SO2, SO3, NOx, heavy metals, dioxins, and so on.
Yeah, very good question. Happy to answer that. PROMECON is not only measuring process gas for cement industry, we are also into the steel industry and other smelter industries. And in these industries, we are measuring with the infrared sensors CO2 content, CO content, and certainly SO2 content is possible. The thing, however, when you talk about pollutants, is the levels. We are a process gas measurement company. So when we're talking CO measurement, we're measuring 2%, 5%, or 15% CO in a steel plant. Yeah, we're not measuring ppms. That's way too small. So if you want to know SO2 on a large level, on a percentage level, that would be possible. If you are talking SO2 on the stack at ppm level, that's not. We're not SEMS. We're not doing SEMS. We're really focused on process gas only.
Okay, excellent. Now, obviously, throughout your presentation, you mentioned a number of different applications in the cement production process. Where do you I suppose, where do you typically see most demand for your systems? And is there a single area where you could pinpoint and say that's the one you should prioritize in terms of, I guess, impact?
Well, I've given you all the highlights, but if you want to now know what is the top of the iceberg, that's pretty much downcomer, I think. Downcomer, because you have a large ID fan, you have the whole pyro process. I would say downcomer, raw mill. I mean, these are the big ones. But recently, we have a lot of waste heat recovery. It's a bit of what people have as actual problems. But you start gas flows where you have the largest fans or even a pyro process connected, then these will be the big ones. I would probably say downcomer, raw mill, TAD. These are the real big ones.
Okay, and for these types of applications, do they what's sort of the ROI period like for these installations generally?
Well, the lawyer's answer is it depends. But okay, I've given some examples, and I think what you can always relate to, just take the big bombers that you can try to attack with this. One is, for example, if raw mill and downcomer, we're talking fan. So you look at your fan rating. How big is your fan? Is it a variable frequency controlled one? Then it's easy. Then it's a third order of magnitude. So we're talking 20% fan power savings.
Okay.
If you have a pitch control, it's a little bit less. It's 15. But then you see, is your cement plant located in Germany, where we recently had electricity prices of 800 euros per megawatt hour? I mean, in this case, it's a killer, yeah. But or are you in a country around the world, somewhere in Kazakhstan or somewhere where power is much cheaper? Then the calculation is different. So taking these rough things into, and then the other thing would be fuel savings. How much fuel saving? A few percent fuel saving. How much does that mean to you? If you have secondary fuels and you have negative fuel costs, you don't care about that. So you care about the electricity. But if you have petcoke or you have to run, fuel costs, then of course that's another thing. So I think the typical ROI for a measurement from us is always in a couple of months. I mean, you will not have to wait for years. But you can make your own calculations pretty easily. Usually, if you attack the big parts, it's a big chunk you can save. Okay,
excellent. Now, I mentioned specific systems last time, but almost turning that on its head. When you're speaking to customers, do they typically go for one process, or do you apply the technology to the entire plant? How does this typically? What's the typical demand you see from customers?
Well, we have a couple of clients such as Holcim that are optimizing their plants, and they have specific points where they optimize. And one point is the kiln. So from such clients, there will be always the same measurements demanded, because they know exactly how to do it. They put it in, they connect it, they have an expert system or a machine learning system, and then with that and that additional control point, they can converge to a lower process node. It's much easier, and they save money immediately. So, like I said, you can apply to the whole plant, even to finished product mill. If you have finished product mill, you would like to save electricity, or you would also have a better control of your fineness, which is also connected to the gas flow through the kiln. Or you would like to have a better control of filling level. Many finished product mills are still tube mills. So it depends a bit on where you're coming from. There's applications everywhere, but as I mentioned, the top three I would say is downcomer, raw mill, and TAD.
Okay, and looking ahead, I believe sort of towards the end of your presentation, you mentioned waste heat recovery applications. Would you say with the ongoing pressures towards decarbonisation that waste heat recovery is perhaps the biggest growth area for this kind of technology?
At this point, yes, and I'm sure there will be more things coming, such as CO2 sequestration. The sequestration is only, let's say, most effective and efficient if the CO2 levels are high enough. Sure. So as we are measuring CO2 levels in the steel industry easily, that could be another exciting application to talk about one of the next webinars. And certainly if there's a plant or a large OEM, we have a couple OEMs asking for this already, but now's a good time to do maybe a pilot on this, because I think it's going to be a very big application field, cleaning up the flue gas from CO2.
Okay, excellent. Well, Hans, I think now is a good time to draw things to a close this afternoon. So thank you so much for going through your presentation and going through those questions with me as well for our audience.
Thank you.
And of course, I'd like to give a very big thank you to our audience today as well. Now, before we do end today's session, I have just 2 final notices for you. I mentioned this a little bit earlier, but please do keep an eye on your inbox, as we'll be following up this webinar with a link to access an on-demand version, so you can go back over today's presentation at your leisure and review anything you may have missed. And secondly, just to remind you all very briefly that discounted early bird rate tickets are still available for Envirotech, which is taking place in Athens, Greece in March next year. So do head over to worldcement.com/Envirotech to book your tickets. So thank you again, everyone, for joining us today. I hope to see you all again soon. Goodbye for now.